having the wave equation for if you're in a field with a source. So previously you might have learned about how to derive the electromagnetic wave equations for if there aren't any sources, the homogeneous wave equation, and how to solve that. But today we're going to be looking at if there is a source and how you would go about solving the wave equation in this way. And this is useful for example, if you're studying like antennas, where obviously when you're dealing with an antenna, there's a source, which is the current that's going through that antenna. And the way that we're going to do this, solving these equations, is we're going to introduce a new vector field called a potential vector field, or like you can think of potential in the same way we like the word voltage. Potential is kind of like representing energy. It's kind of a field that represents energy. So we're going to be deriving this separate potential field to simplify the math and make it easier for us. But the potential field itself also provides new sort of insight into what the electric field is and helping us understand it, especially when we're dealing with a source. So first, we're going to start off by writing down Maxwell's equations. The divergence of E is equal to rho over epsilon. Divergence of B equals 0. The curl of E equals minus J omega mu, or sorry, is equal to minus mu partial H over partial T. If you don't know what H is, it's called the magnetic field intensity. It's related to B by pretty simple. Well, I mean it can get more complicated, but in isotropic system, linear system that we're looking at, you can relate B and H by this equation. So curl of E is equal to minus mu partial H over partial T, and the curl of H is equal to J plus E partial E over partial T. Great. So these are the Maxwell equations as we have learned them so many times in the past. And normally when you would want to solve this now to derive the wave equation and then solve that to get the EM wave, you would set rho equal to 0 and J equal to 0 because that's how because we look at like a vacuum with no sources to derive those equations. But now we're going to try to explore and understand how to solve these equations when there are sources. So first what we're going to do is we're going to try to derive the wave equation as we would have as if it was a homogeneous solution. And the way you usually do this, if you've done this derivation before, is you just take the curl of the third and the fourth equation, right? So the curl of E, which there's an identity that says that the curl of E is equal to the gradient of the divergence of E minus the Laplacian of E. And this equals minus mu times the derivative with respect to time of the curl of H. Since we have to take the curl on both sides, right? And let's do some simplification here with this equation. So we know that we can do some substitution. We know that the divergence of E is equal to rho of E, so that you can rewrite this as the gradient of the charge density over epsilon minus the Laplacian of E is equal to And we can substitute here j plus epsilon gradient e over partial e over partial t, so that we get the equation minus partial j over partial t minus mu epsilon partial squared e over partial t squared. Great. And let's now rearrange this so that it looks more familiar to us. We can say that the Laplacian minus mu epsilon gradient squared e over gradient t squared is equal to minus partial rho over epsilon, or sorry, not minus. Let me erase that. Sorry, positive rho over gradient rho over epsilon plus mu partial j over partial t. Great. And this should look familiar to us. This is kind of like the wave equation we've seen before. You know, this is even like 1 over c squared, except it's a inhomogeneous equation because we have these parameters on the right-hand side. Now we're going to do a similar thing for the for h. So we're going to take the curl of h. And that gives a very similar expression to here. Right here. Except instead of E, we're dealing with H. So that this is the gradient of the divergence of H and the Laplacian of H. And this equals, this should equal the curl of J plus epsilon times partial over partial t of the curl of E, which we know from here to be just minus mu of partial h over partial t. Great. And we can do a similar thing as we did above and try to rearrange this equation so it looks more familiar to us. So this term cancels out because the divergence of a magnetic field is 0 because there's no magnetic monopoles. And so we can say this is gradient squared h minus mu epsilon partial squared h over partial t squared is equal to the curl of J. Great. So you can see now that we have two inhomogeneous equations, inhomogeneous wave equations, one for E, one for H. And the reason that we can't solve this is because they're still coupled, right? There's still like a J term that's in both of them that makes these equations coupled to each other and not separate, which makes it incredibly difficult to solve. And so the way that we've been able to get around this is by introducing something called potential fields. The way that we get around this, the way that we get around this issue of how to solve these coupled inhomogeneous equations is we're going to introduce an auxiliary potential field that I was talking about previously. What that means is if you've taken multivariable calculus before, you'll know that something like this, the divergence of B equals 0, is an interesting property for B because it tells you that there has to be some vector field out there whose curl, A, whose curl is equal to B. That's what if a vector field has this property, divergence of b equals 0, then that means that there has to be some vector field A whose curl is equal to b. That's kind of a property of that you learn about in multivariable calculus. And so that means that H, which is the field that we're looking at, would be equal to 1 over mu part of the curl of A. And then more so, looking at that further, we can see that what we can do is we can look at this equation, this Maxwell equation, and we can, here, I'll move over here for some more space, but we can say that then the curl of E is equal to minus the curl of A, or sorry, of derivative of A with respect to time. And then that can be rearranged to curl of E plus partial A over partial T equals 0. And why this is interesting is because just like the divergence of B equals 0 has this property, the curl of E plus partial A over partial T equaling 0, that's also a unique property of vector fields because it tells you that there exists some scalar field, call it phi, whose gradient is equal to E plus partial A over partial T. Or in other words, or I should say minus phi, because when we think about electric fields, we have to think about how we have to think about them in the opposite due to current convention. But anyways, so and then this can be rearranged so that we can say that E, the E field is then equal to minus partial A over partial T minus the gradient of this phi scalar field. And so this is kind of like, basically what we've done here is we've introduced two new auxiliary potential fields, A and phi, and we will solve the wave equation using these instead because they'll allow us to uncouple those equations which we had seen previously, and then from there what we can do is we can just plug these auxiliary equations back into auxiliary fields back into these equations to be able to get E and H. So almost kind of a diagram used to describe this is like we have Maxwell's equations, Max's equations, and instead of going directly from here to EH, we're gonna use these helper functions, phi and A, and then we're gonna take the derivatives of them as you see here, as needed, the curl, the gradient, and the time derivative to get E and H, right? And so this might seem like extra steps, but these helper functions will simplify the whole solving process to make it easier to solve E and H. And I should mention, once again, like we're going to think about these as strictly mathematical terms, phi and A, but in reality, these are like, they're called potential fields because they have, like, they represent the energy in the system, and so they are their own, like, they have their own physical significance or physical meaning that you can think about as like sort of how the energy in the system propagates. But for now, we're going to think about them as like strictly mathematical terms. Okay, cool. So now, instead of doing the curl of E like we did previously, let's do the curl of A instead. Or actually, Okay, wait. Sorry. So, sorry. Got ahead of myself here. We're gonna do. So we know that the equation curl of h is equal to j plus epsilon partial e over partial t. So what we're just gonna do is we're just gonna substitute our equation for h, which we know is gradient a, curl of a, or I should say 1 over mu times the curl of a, which equals j plus epsilon partial e over partial t, and the e will replace with our new auxiliary equation, partial a over partial t minus gradient of phi. And then you'll notice that we have this similar curl of a, which we can rewrite using the identity we know, which is that the gradient of the divergence of a plus minus the Laplacian of a is equal to mu times j plus epsilon mu partial squared a over partial t squared. And wait, I think that's supposed to be a subtraction sign. Yeah. Minus epsilon mu of the gradient of the derivative of phi with respect to t. And we're going to rearrange this equation a little, so we can rewrite this as the gradient of the divergence of a plus mu epsilon phi, partial phi over partial t, and this is just factoring, taking this term over to the other side and then factoring it with this term to get us this. Still minus the gradient squared Laplacian of a plus mu epsilon times square the second derivative of a with respect to time is equal to mu j. And then similarly, what we're going to do is, to get the second potential equation, we are going to, the second equation for the other potential field, what we're going to do is we're going to take our divergence equation here and we're going to plug in divergence of E. We can rewrite it as the divergence of minus partial A over partial T minus the gradient of phi and this is equal to rho over epsilon. And then we can rewrite this further as minus partial t of the divergence of A minus the Laplacian of phi is equal to rho over epsilon. Now, these equations might look like just more complicated, but that's where we're going to introduce something called the Lorenz gauge. So you might have noticed that we're dealing with these second order partial differential equations for these fields, these auxiliary fields that we ourselves have defined. And so we're going to do something which is called, we're going to define a gauge, which is basically like, kind of a simplified way of thinking about this is in when we do second order ordinary differential equations, we have the ability to we need to define like our constants for the solution, right? So when you do a second order differential equation, you need to provide an initial condition for the initial condition, which is basically an equation in the first order, and then a second initial condition for, and then another a second initial condition, and then only once you have two initial conditions can you really fully solve a second order differential equation. Similarly here, because we're dealing with a second order differential equation, we have to define a gauge, which is kind of just like a more advanced concept of that, which is basically an equation which will help lead to a solution. So in this case, there's many different gauges that you can use, and each is kind of like just a different way of thinking or understanding the solution to the wave equation. But we're going to define something called the Lorenz gauge to simplify this, which is a Lorenz gauge. A Lorenz gauge. And what this is, the Lorenz gauge is defined as the divergence of A plus mu times epsilon times partial phi over partial t equals 0. Now, this might seem kind of weird, like we're just defining an equation, but it's basically because we have a degree of freedom that we're not using, right? So, like, again, kind of alluding to the analogy of like a second order differential equation, we have 2 degrees of freedom, which is why we need 2 initial conditions. Similarly here, we kind of need 2 conditions to solve our equation, which is why, and we're using the second degree of freedom to define our gauge as this, because it will, as you'll see, greatly simplify our equations. And you can kind of see exactly how it'll do that, because it'll completely cancel this out, since, you know, the gradient of 0 equals 0, and then it'll simplify this equation because we can now rewrite this as now as, and I'm skipping some steps here, but as the Laplacian of phi minus partial squared phi over partial t squared equals minus rho over epsilon. Great. And then for our other equation, we can rewrite it now as gradient squared A minus mu epsilon partial squared A over partial t squared is equal to minus mu j. And what you'll notice now is that these new equations that we've arrived at are still inhomogeneous equations, right? It's not 0 on the right-hand side, but they're uncoupled, which is to say that there's no variables in one term that are in the other, which is incredibly valuable for us because it means that we can actually solve them. If you're taking a PDE course, you know that there is a solution to the inhomogeneous wave equation. And so that's what we will do in the next video. Now that we've derived these wave equations for these potentials and we've derived how the electric field is related to these potential fields, in the next video we will look at how we can now solve these 2 equations that we've derived. Thank you so much for watching the video. If you enjoyed, please like and subscribe. Thank you.